Okay, so we're going to start into chapter 5, which is bonding. Uh, when we did Gen Chem, we looked at like homonuclear diatomic molecules. We looked at the molecular orbital structure, and that was all straightforward enough. Now we're going to go into it at a much deeper level. We're going to see that molecules do things that we didn't talk about in freshman chemistry because just weren't ready for it.
Yeah.
And you're going to find out. You remember how we had like the sigmas and the sigma stars and the pi's and the pi stars? Now you're going to find out you still have those. You have pi structures and sigma structures, but they're going to be so complex now that you're going to have to go by energy level and symmetry of the orbital to explain the molecular orbital structure.
There's no like simple representation.
Not anymore.
Cool.
Okay, so we're going to start out with hybridization and kind of look at some we know and some we might not have seen before. So, okay, let's talk about what hybridization is versus what it's not. Hybridization does not mean that these orbitals in the molecule like physically show up like this. Okay. What they are is a scheme to explain what is actually happening with the electronic structure. Because in a molecule, the electronic structure is going to be a unique solution to the wave function. Each molecule is going to form its own set of molecular orbitals that house the electrons for the molecule. This is hybridization is a way to kind of explain that. And as we see some of the actual structures of orbitals, you'll kind of get the idea of why this exists. But it also came into being because, for example, with pure atomic orbitals, you cannot get the orbitals to rotate or space themselves in a way that will allow for VSEPR to occur and will still keep the molecules together without the electrons blowing everything apart. So there had to be a way to start to describe this, and so that's where hybridization came in. Because it's like, well, we no longer have the pure atomic orbitals, something else is happening. So they're all kind of blending together into these new structures. And so what you get is you're getting mixing of various atomic orbitals. So this is your LCA. Have for example, your wave function for your sp orbital is going to be a half and half mixture of your 2s and your 2pz. One is so the negative pz comes from the fact that just the direction that the hybrid orbital points.
So you have to have the Z be the primary axis for these as well?
No, it's just because on this one I showed the mixing of 2s and the 2pz orbitals.
Oh.
So you could also do it, you could change these from pz to well, the bottom is also pz, but let's say you used like a py axis, then you would just change that to py. A lot of times in chemistry, Z is the axis that's used, especially for inorganic chemists, because for example, that Z axis is like where your principal rotation axis goes. It's just kind of the way that inorganic chemists understand things. Okay, so this is going to be a little different than something you've seen before. So SP is a scheme for linear species. How do we get the valence electrons that exist in all the atoms to work in a way that they actually form these bonds? So here, you see we have beryllium BeH2. And you see you have these sigma bonds that are forming. So remember, your sigma bonds are your head-on bonds. You get that head-on overlap. And you see beryllium sp hybridizes to get its electrons in just the right way to then be able to hybridize. Oh, I could do like a really nerdy moment. Did you ever watch Power Rangers? Kind of like how all their robots will like change to then all fit together to form the super robot.
Oh,
Yeah.
I've seen memes about it.
So they have like the individual robots and
Yeah. Oh, okay.
the,
Everything makes sense now.
yeah. So it's like we went from atoms to the mega molecule. But let's kind of look at what's happening now. Before, when we talked about beryllium, we would draw the 1s and 2s structures. But since beryllium has entered the n equals 2 regime, we also have 2p available. Okay, so these sp orbitals, they're going to be somewhere between the 2p and the 2s energy wise. Okay, and so what more or less happens is you have to start freeing up electron pairs in order to accommodate the bonding that's going on. Because you notice your beryllium has that pair in the 2s level. So whereas in Gen Chem, what we would do is we'd just say, oh, you have those two valence, so let's make the sp orbitals and just place those valence within the sp orbitals. But there's a problem when they're paired, they have their anti-spin.
Mm-hmm.
Oh, but that's going to start to become problematic when we want to place those in the sp orbitals, especially due to maximizing the multiplicity. So again, you see how in the sp orbitals we have the two unpaired spin up. So that would be a triplet multiplicity. So in order to achieve a triplet multiplicity, the molecule is going to have to go through kind of a shift into a triplet multiplicity, where you actually are going to start to get beryllium 2s, a 2s electron promoted energetically to the 2p subshell, which will then fall quickly into the sp hybrid.
And so then they're no longer. Oh, okay, I see.
Yeah. So this is a more accurate representation of what's happening rather than just, we'll count the valence and then put the proper valence in the sp orbitals. One of the rules, like we talked about in freshman year, if we use n atomic orbitals, we have to end with n hybrid orbitals. So again, your sp uses the s orbital and one of the p orbitals. And so since it used two orbitals, you have to get two orbitals for the sp. Another thing that you can think about is, since the sp is taking on about half p character, one of the electrons have to start to access that p level. So that's another reason for the promotion of an electron into what we would typically call an excited state. It just doesn't live there for very long. It just kind of migrates through there into the sp level. Okay. Here's an idea. Here's the scheme for our sp2, or trigonal planar spacing. And so these wave functions have to do, so first off, they're normalized. So when you take the coefficients, they should all get you to one third of the character comes from the s orbital and 2/3 of the character comes from the p orbitals. The way these are set up is like, you see how the sp2 along the x-axis has 2/3 for the px. Okay, well, fine. That gets you to 1/3 for the s and 2/3 for the p. But that right there, so that sp2 orbital lies right along the x-axis. You see that at the top?
Yeah.
So right there, that lies right along the x-axis. So we don't have to take account of, like, xy components. These down here, these start to take account of xy components. That's why you're getting a mixture of p and of x and y. So as you see, so those are going to go right between those, right between the xy axes. And they're going to point a little bit more towards the Y, so you get 1/2 Y and 1/6 of X character. So as you look at these, you can use the diagram to start to understand why these wave functions map out the way they do. But the point of the wave functions is not necessarily for you to, because these are generalized. You don't actually know what psi is. We haven't done that yet. That would be something more for like a quantum chemistry course. But the where was I going with that? Well, the main point is that you're seeing that you have these atomic orbitals, and molecules are going to take these atomic orbitals and combine them in different ways to produce what actually become the molecular wave functions.
Okay, so question, like how, when you say it has like a character from S versus character from P, like what exactly does that mean?
So your S character is spherical, your P character is this dual lobe system.
So it's just the shape kind of?
Yeah.
Okay.
And so it's taking a little bit of the character from each one of those, and it's producing this new hybrid orbital where you see you have a big lobe and a small lobe. So you're getting that P character, but then you're also getting a larger lobe, which is taking on some of the spherical S character. So that's what that means. Our next type of hybridization, and again, you see your 4 wave functions, or about a quarter from each one. Well, you could say 1/4 from each one of these, or 1/4 S and 3/4 P, which makes sense. But again, you're getting the same kind of character, and this is for a tetrahedral regime. Now, we're not really going to go through this, but you remember that this is always going to match the electronic configuration. It doesn't always match the molecular geometry based on if we have lone pairs or whatnot. But your sp3 is going to be for a tetrahedral regime. And again, you get your mixing of your S and your P orbitals to get the 4. And here's the thing. All of your hybrids are at the same energy level. Do you remember what the word for that was?
They're degenerate?
Degenerate. So for the standard for our trigonal bipyramidal geometry, we have the SP3D. Now that one we kind of talked about, but there's different versions of it based off what you need. Your standard the P character in there where, it's like you would have, so like here, you might have a PZ mixing with your DZ squared. And then you have your PX and PY mixed with this circular region around the middle to give you your circular region around the middle. Okay, so this is your standard trigonal bipyramidal combination. But here's an example of where we would actually need an sp3d combination where the dx squared y squared is the predominant d orbital that's used for hybridization. And this is your square pyramidal. So again, that would be your octahedral, but a ligand has been removed for a lone pair. So can you see why the dx squared minus y squared might be more important this time as the primary D constituent?
Yeah, I can. So it's like more flat along.
Mm-hmm.
How do you, wait. What about the top and bottom ones? Are they still from the P?
Yeah, so
SPZ? Or Wait, PZ? Is that a PZ orbital?
Yeah, you would get a little bit of that character in there for that lone pair. Um, the character we're predominantly worried about is ligand binding.
Mm.
And so in this case, you see we have those four radial ligands that are going to be along our individual coordinates. And so getting that the predominant dx squared minus y squared is going to allow for a better bonding of those. And then the lone pair will go into an orbital structure. Again, it's going to make more sense because I've prepared some molecules with actual molecular orbitals. So you can start to see what those actually look like, because you'll see that they have all these characters, but the orbitals themselves are unique to the molecule. This is just kind of a scheme to say, well, how do we get this ligand field? So one of the things to think of in inorganic chemistry is, yeah, there's going to be lone pairs. What we're predominantly worried about is ligand fields. Mm. And so this one has that square pyramidal ligand field. I think that 2 should have been a superscript, but okie dokie. But this is your standard sp3d2. Yeah, if you see down at the bottom, I just accidentally hit the underscore instead of the caret mark. But here you see we have chromium hexafluoride. So a nice, a nice standard octahedral geometry. And so you're going to get a combination of your S, all three of your P's, because you see your PX, PY, PZ coming into play. And then your D's, you're going to get a good mixture of dx squared minus y squared and dz squared. Because you can see how both of these are going to be valuable, and especially since we're using a metal. Those D's they're available, they're going to come into play. And so here you see 3 actual solutions to the wave function. These three are degenerate. And if you notice, these actually make up the 6 lobes, if you put them all together, of your sp3d2 orbital set. But you can see how we're getting like a little bit of a larger lobe, where then it stretches out, it forms the sigma bond. So these are actual solutions to the wave function for this octahedral geometry. So you can start to understand, well, if these are solutions for bonding, and these are unique to this molecule, well, how could I model this? All right, well, I'm getting so this is where they start to come up with the sp3d2 model to try and explain what's actually occurring. Because again, before computers, you don't want to sit there and solve that wave function by hand.
Yeah.
Now here's one we didn't cover in Gen Chem, sp2d. So this one is for your standard square planar molecule. So the one we predominantly studied in Gen Chem was xenon F4. I made this one off krypton tetrachloride. And you can see, so if we combine our s orbitals, our px, py, and dx squared minus y squared, because again, this time the dz squared is not really that up and down low with the dz squared. It's not going to have any interest for us. But look at some of these molecular orbitals. You can see the hybrids in there. But these are the unique solutions to the wave function for different energy levels. The 2 on the right are degenerate. The 1 on the left is lower in energy. But like, look at that one on the left. You can see a very large combination of S and P, probably, and really SP and D, and that's why those lobes reach out as far as they do to hit the chlorines. And then on the top, you can see a lot of that D character coming in to get the larger lobes at the end, reaching way out to grab those chlorines. And these are all sigma bonds. That first one is almost a total sigma bond for the whole molecule. And the other 2 are going to be directional bonds. But if you start looking at these actual electronic structures, you can start to see the P and D orbitals that are necessary to form this. Now the fun begins. Multiple bonding and polyatomic molecules. So I just figured we'd start with something we've seen before, ethylene.
Okay. Ethylene.
Yep, so let's just do our basic analysis of this way we did in Gen Chem. We'll start there. So while we have a double bond, so it has to have a sigma and a pi bond. Each carbon will be sp2 hybridized. Hydrogens will not hybridize because they only have the one s orbital. And so if we look at this, our carbon starts like this. It's going to give us those three sp2 orbitals and a 2p orbital. So the 2p has to have an electron left in it. And then the sp2 orbitals have to make room. So again, this is kind of what we did in Gen Chem, where you take your 4 valence and say, I have to make 3 sigma bonds and a pi bond for each carbon. And so this is the way you would set up the box diagram. And then, of course, your hydrogens, that's not a very good p orbital. Sometimes my circles are so bad, not even this enough of them drawing them. But here, like you would get your 1s orbital and an sp2 orbital forming a sigma bond. So this is really how we went about it in Gen Chem. So we start to understand the bonding involved in ethylene. However, it starts to get much more complex if we want to think about, like for this one, in Gen Chem, you couldn't have done the molecular orbital structure. It's just too many atoms, too complex. I brought this back because I want to make sure we remember this. Okay. This is how we assign molecular symmetries. Now, when we're looking at orbital symmetries, we're not going to go through every one of these because let's take a look at ethylene. Okay. Ethylene is a D2H molecule. So you see how up here we have primes, we have A's, B's, E's, T's, 1's, 2's, G's, U's. Now, when you're looking at the symmetries for the orbitals of a molecule, you are limited to the symmetries in the character table for the molecule. So you see, I can't have any A primes. I can't have any A1s. I can have B2s. I can't have B primes. So these are the symmetries I'm limited to. Then we want to, so this is where we start to talk about the symmetries of the molecule. That first one up there is lower in energy. So if you were doing the full molecular orbital configuration, and so I probably should put those in a better order because we usually go bottom to top for higher energy. The one on the top is lower energy than the one on the bottom. First off, looking at it, can you tell me why? Why would that one be lower energy?
Why would that one be lower energy? Because the bottom one's a pi bond, right?
Pi structure.
Mm-hmm.
And the top one is
sigma
structure. So again, looking at that, your sigma structure is between the 2 carbons. Mm-hmm. And then your sigma structure is so you see here, you incorporate carbon and the hydrogen. You're actually getting the sigma structure in there, but since each hydrogen has its s orbital, and then you're getting these sp2 orbitals, you see this actually comes together to form this larger structure. This is why it's more complex when you're actually looking at molecular orbitals, because that is still a sigma structure for each carbon hydrogen. Mm-hmm. They've just come together to form a single wave function. And so this is your carbon-carbon sigma bond, and then on the bottom you have your pi structure. Okay, now to assign symmetries, you notice how A or B is symmetric or anti-symmetric with the highest order axis or the principal axis. Well, now this becomes problematic Because look at this. What's the highest order axis? Well, let me go back up to this so it's easier to see. What's the highest order axis here?
C2.
C2. What, which direction does the principal axis usually lie? Along
Z.
in the Z direction. Do you know the Z direction for this molecule?
No.
Okay, so this is something that you kind of get used to over time. The standard practice for the C2 these principal axis is down the center of the bond. So that would be your standard practice for your principal axis for ethylene. So we always try to go by standard practices. So if you're talking to someone from anywhere else, you're speaking the same language.
Sure.
Now, keeping that in mind, look at these two. Can you tell me the symmetries of these?
The symmetries of these.
These molecular orbitals.
Gosh. Okay. I would say that the first one is A, and that you didn't want to do the primes and everything.
We can't because we're limited to the symmetries in the character table.
Yeah. Okay. A, and I would say it has A1G.
And we can't have a 1.
Oh, so just AG then?
AG. Now, if you're reading articles or whatnot, this is how they do orbitals. It took me the longest time to realize these were the same thing because I didn't have someone teach me this. But the way they do these in articles, they use lowercase. So this is an AG symmetry. Look at the pi structure. What do you think?
I would say.
So is it symmetric or anti-symmetric due to rotation around that principal axis?
It's got to be B1G.
It is.
Okay.
So as we're talking about molecular orbitals, and so let's say you were drawing the something like this where you have all these structures in the middle. Something crazy like this.
Sure.
Because you'll see that later. These are all going to be so that like your your AG, B1G, stuff like that. So this is how you're going to start to understand molecular orbital structures. That is a really rough diagram, but I think it's a point across. But now I want to show you something that's going to be new to you.
Oh.
HCN.
Okay.
Look at that character table. This is a C infinity V point group. First off, why do you think it's C infinity V?
Because it can just keep turning.
Yeah, your principal axis right there.
Yeah.
That's a C infinity axis. Because it doesn't matter how you rotate it, it's always going to be the same.
Yep.
Now, and then of course it has vertical mirror planes. So the C infinity V, it has these different symmetries. So sometimes your A1, A2, E1, E2, E3, so on and so forth. And now these are going to be put with, and honestly, no one ever taught me why this is the case, because usually these sigmas, pi's, deltas, phi's are used for term symbols for diatomic molecules.
Oh, cool.
But this is not a diatomic molecule. If you take when you take pChem, we'll cover term symbols a little bit, because term symbols tell you about the spin of the molecule, the total angular momentum of the molecule, and spin orbit coupling, stuff like that. But what these mean is for some of these unique, like high symmetry point groups, they use these different symbols. So I've kind of given a list of what they mean over on the side. Because again, these bugged me for years because no one actually taught me this. I was in a computational quantum lab, not a inorganic lab, so I never got this.
Mm.
And you can notice the different symbols. They're looking at the symmetry differently. They're inversion, nodal planes, stuff like that. Stuff you've never brought in before. So I didn't want you to look at a character table like this and go, what do all these Greek letters mean? Well, it defines a symmetry.
And is it because it's C infinity, or is it C, like, could I apply these to any point group, or is it?
Usually you only see these on your really high symmetry point groups. And also usually, I'd have to look. I think these really I've only really seen these on like C infinity character tables. Okay, so let's actually take a look at real molecular orbitals from this molecule. Okay. So now if we look at this, so let's start to take this apart. We know that in the triple bond, we're going to have a sigma bond and 2 pi bonds. That means the nitrogen, when you take it apart, is going to be sp hybridized, where it gets sigma sigma because it's a sigma over here. So I have to have those p orbitals available. The carbon will also be sp hybridized. And nitrogen's going to have a log. So we know that those p orbitals are going to form the pi bonds, the sp orbitals are going to form the sigma bonds, and the H will use its 1s orbital to form a sigma bond. And then we start getting unique structures like this. So you can see the pi structures up top. That one in the bottom might throw you a little bit.
What's the one where it has 3? Is that E? No.
No.
Am I crazy?
E is a doubly degenerate.
Doubly degenerate.
So 2 orbitals that are of the same energy.
Mm.
But it also, you can link this. So look at those. Do you see between them? There's a nodal. There's a node.
Oh, it's the delta one.
Not delta.
Oh.
So each one has a single nodal plane.
Oh, okay. For those 2. Okay. So is it the pi?
These have to be the E1 pi.
Okay. Okay.
So these are at the same energy. And each one has a single nodal plane. Those are your E1 pi orbitals. Now, again, when you calculate these, I get these orbitals in lists of numbers. So in terms of electron volts, and these 2 are the exact same energy. This one on the bottom, even though it looks unique, I want to see if you can figure out what its symmetry might be, because you're worried about the sigma bond in the middle. It's the only one at this energy, so it can't be an E2 delta, an E3 phi, even though there's two nodal planes there.
So it's probably, how is it the sigma negative?
So let's take a look at that.
Am I crazy?
Well, you would want to call it that.
I would want to call
But
it.
let's look, that's also aligned with A2. So
Okay.
A, so symmetric with respect to that C2 axis. Could it be 2? Anti-symmetric with respect to a second symmetry element? Or is it 1 symmetric with respect to another symmetry element? What if you put a sigma V through there?
Yeah, I guess it would be.
It has to be the A1, and so that's going to be your A1 sigma plus.
Mm.
Now, this has to do with how wave functions work.
Mm.
You're not so much looking at the exact shape of those orbitals. You're looking at the phases. So if you were to invert that or take another C2 and flip it, your phases are going to line up. So that's going to be a symmetric operation. And the electrons will then take the orbital shape they need to fulfill their purpose. So they will adjust to fill, kind of like a fluid filling its container. The wave function has specific energies that are available. The electrons that flow in, even if you did an inversion or a flip with your C2 or whatever, the electrons are going to fill in to match their container. So really, when you're thinking of symmetric versus anti-symmetric, look more at the phases. And again, with this one, the nodal plane, you're not worried about those because this is your sigma bond.
Mm.
And that's why if you calculate this, you see this one standing alone at its own energy level. And so it can't be the delta because there's no degeneracies.
Mm.
So it takes a little practice to start to take these apart and figure out what they mean. Let's look at BF3, something a little more straightforward, a D3H. Okay, so first off, where am I going to take this apart? Oh, okay, so we'll do that later. Okay, so your boron, sp2. Now, okay, this is where you start. So you're at this level now where you're going to see chemists go, I don't agree with you.
Oh, okay.
And so I have to disagree with the textbook a little bit because she said that the F atoms are also going to kind of sp2 hybridize. I disagree because the Fs can rotate in space in any way they need to in order to line up a p orbital for a sigma bond. And you can start to see that when we look at the characters of these. If you really wanted to, and the fact that the Fs themselves are going to have 3 lone pairs. Now, I say it's not really necessary for hybridization. She says that they sp2 hybridize, which I guess you could, where the p orbital itself gets a lone pair, and then the hybrid orbitals each get lone pairs. The reason I say it's not necessary is because even if you, well, there's also plenty of arguments for her reasoning too. There's arguments both ways. Because in hers, you can get some electrons further apart for if you sp2 hybridize the fluorines, but a lot of times your halogens are not known for hybridizing. It's just not necessary. But I guess if you wanted to really play Vesper with each individual atom, you could hybridize the F, put lone pairs in sp2 orbitals. That way, they're only interacting with the 2p electrons and not each other. So there's arguments both ways. It's really going to be kind of up to you to start making arguments to figure out where you align.
Okay.
This is not one of those where you just take my word for it and run with it.
All right, I'll read what she says.
Yeah, read what she says. You know, think about all the possibilities and what makes most sense. Okay, so of course your boron is going to come out with its sp2 orbitals. But there's a problem here because then it leaves a 2p orbital, but your boron has the electron configuration 2s2 2p1. It needs 3 sigma bonds. It has 3 valence, so the sigma bonds have to go there, but I'm out of valence electrons. Okay, well that's kind of interesting because I have a 2p orbital that's left that's completely empty. That's a nice available energy level that's just waiting for electrons. So let's kind of look at some of these structures. Okay, so let's go through And kind of talk about the symmetries of these. So again, we have A prime one, A prime two, E prime, a double prime one, a double prime two, then E double prime. Okay. Let's remember our primes. Are we symmetric or anti-symmetric with respect to a sigma H? Okay. So we have no G's, no U's. So let's look at this first one. That is your lowest energy orbital. That is your overarching sigma structure. So that encompasses all three of the sigma bonds. What do you think for a symmetry? First off, what's its principal rotation axis?
C3.
C3, is it symmetric or anti-symmetric with respect to that axis?
Wait. Is it anti-symmetric? Wait. No, it's symmetric.
It's symmetric, so it has to be an A. Now, 1 or 2, is it symmetric? So where are your C2 axes?
Down every bond.
Yeah, so would it be symmetric or anti-symmetric with respect to that C2?
It would be symmetric.
So that's a 1. Now, is it symmetric or anti-symmetric with respect to a sigma H?
Symmetric.
Symmetric, so that's a A1 prime.
Okay.
Now, what do I do here?
Now, wait.
These look a little different, but in reality, what does that mean? What do those numbers mean?
I mean, they're degenerate.
Mm-hmm.
Okay, so they're going to be the same thing.
So what from the character table do you think represents that?
Um,
And I want to tell you that this is also in the so you're going to start to see this in the molecular orbital structure. This is a 3 A1 prime because you're going to have multiple A1 primes, and the lower energies are like 1, 2. This is like the third one up. Okay. The others are more centrally located on the individual atoms, so they're very tiny orbitals. So when you see this, that's what that means. This is just your third A1 prime in the energy structure. So look at the character table. We have 2 orbitals with the exact same energy.
yeah.
What kind of symmetry is that going to give?
Are they okay? Are they going to be A's again?
Mm-mm.
No, they're going to be the E's.
Doubly degenerate.
Okay.
Because remember, if we go back up, your E is a twofold degeneracy.
Dang, I need to memorize that.
It takes time. This is something brand new. This is quite a bit harder than the material you've done. Okay, so we have an E. Oh, did I write down what this one is? Oh,
And I'm gonna guess the one on the left is double prime and the one on the right is just 1 prime.
well, they're going to have to be part of the same E.
They have to be the same E. I guess if we're looking down that.
So remember your primes. Okay, so there is no 1 or 2 for the E's. So we can't look at the C2 axes and talk about symmetry. The primes have to do with the sigma H.
Okay. So I guess, yeah, they are symmetric with the sigma H.
So that's just a single prime.
Okay.
So these are your E prime orbitals. See, I can still do it even if I don't write it down. Now, see, they look different.
Yeah.
But it's that degeneracy that dictates.
Mm.
But let's start to look at what happens down here. Now, here we see a higher energy sigma structure, boron out to the fluorines. So we already had a sigma structure. What do you think the symmetry is on this one? So do the C3 axis. Is it symmetric or anti-symmetric?
It's symmetric.
So it's an A.
Okay. A2 prime.
Well, so then this would be your 4 A1 prime. So you kind of see how that works?
Yeah.
Because that's higher in energy than the 3 A1 prime.
Okay. Okay. And
now,
how do I know that they're
So let's look at what's okay. We predicted 3 sigma bonds. Do you predict any other interactions?
I mean, you said something about the empty p orbital.
Uh-huh.
Like, is there gonna be some sort of resonance kind of thing going? No,
Oh, no, there is.
there is.
And so this is something you would never have guessed in Gen Chem. What kind of character do you think is going to start to develop?
Is it gonna be kind of like a pi bond?
Yep.
Okay.
Look at those two. These are unique wave function solutions, molecular orbitals. You can see a very clear pi structure. The one on the top right shows a pi structure between the boron and the fluorines, more localized versus you actually, that one on the bottom left, you actually start to see some delocalized character. So let's see if we can get the structures of these. So what this would, that's your 2e prime. Okay. Okay, now I will tell you that the one on the top right has another, or I just didn't put it on here, has another orbital that's degenerate with it.
Okay, so it's E.
It has to be E.
And it's gonna be prime.
Prime. That's all we can do.
Okay.
So that's your 3e prime. Because again, we're limited to the symmetries in the character table. Let's look at this other one here. This is a standalone, has its own energy.
Yeah.
So C3 axis, symmetric or anti-symmetric?
Symmetric.
A. C2 axis, symmetric or anti-symmetric?
Symmetric. Wait,
Look at the phases.
no, they'll switch. So it'll be 2.
2. Don't try not to look at shapes. Try to think phases.
Yeah. Okay.
Now, sigma H, symmetric or anti-symmetric?
Anti-symmetric.
So that's a,
double prime.
this is an A2 double prime. This is your first one. So, and we'll talk about this more next time. I want you starting to think about resonances that can occur, because when you actually do the calculations and you look at the molecule, there is very, very clear pi activity in this molecule that you wouldn't have predicted otherwise.
Yeah.
Just straight like hybridization or valence bond theory, you would have never predicted pi structures here, but they're there.
So is that part of the reason why you wouldn't think that the fluorines are hybridized, or like is it just totally separate from that idea?
So again, there's arguments back and forth. Even with the sp2, there's still a 2p orbital there that can become part of a pi structure. So again, I just don't see the absolute necessity for hybridization. She says there is. So again, this one's going to, you need to look into some stuff and see what you think. This is not like a hard and fast, take my word for it kind of thing.
Yeah, for sure.
So read this. So this is kind of a small section, but look into it. Look at what she says.
Yeah.
And see what you think.
Okay, I will. Right.
So yeah, I told you it starts out